Okay, so this is the second video on section 14.6, which is about the directional derivatives and the gradient vector. And let's remember, in the previous video, I explained the following thing. Given z is equal to f of xy with some unit vector, and then the directional derivative of the function in the direction of u is computed in this way. You compute the gradient of f, that's given in this way, and then you take the dot product with u, and that is written this way. And then this was called the gradient vector, and then this is called the directional derivative, and the directional derivative is a rate of change in the direction of u. And if u happens to be 1, 0, directional derivative is just a partial f partial x. And if u happens to be 0, 1, the directional derivative is just a partial derivative with respect to y in the direction of y-axis. Okay, so that's what we did last time. Then now, today, let's look at, today what we're gonna do is basically to look at the gradient vector from more geometrical point of view. And to think about it, what we're gonna do is to maximize the directional derivative. Maximize the directional derivative. So here's a question. Given y is, I'm sorry, z is equal to f of xy, and given this, and then find a unit vector u such that the directional derivative at given xy is maximum, namely as big as possible, and for that u, what is the maximum value? What is the maximum value? Well, here's the way to think about it. So as I put here, the directional derivative for an arbitrary u is given by f of x, the gradient dot product with u. And of course, dot product is computed in this way, but there is another way of computing the dot product, namely that is the magnitude of the first vector times the magnitude of the second vector and the cosine theta. That is another way of expressing a dot product, where theta is the angle between those two vectors. And now what is this? Well, u is a unit vector, so the magnitude of u is 1. So therefore, the magnitude of the gradient and the cosine theta. And then cosine is always between -1 and 1. So that means, this implies the directional derivative is between -1 times this and 1 times this. So negative, the magnitude of the gradient and here. Okay, so therefore, the maximum value of the directional derivative I'm sorry, I just got a phone call. So the maximum value of the directional derivative is this guy. Here. And then this happens when what? Well, this happens when cosine is 1, which means that theta is 0. Meaning that the gradient vector and u have the same direction, namely those are parallel. And you are parallel. So what does that mean? That means u is the unit vector with the same direction as the gradient. So that means u is computed as, now we have seen this multiple times. If you have a vector and if you want to get the unit vector with that direction, it's written this way. Okay. So that's the answer to this question. So for example, let's work out an example. Let f of x be x e to the power of y, and then now find a unit vector u such that the directional derivative is maximum at this particular point -1, 0, at x is equal to -1 and y is equal to 0, and then find the value. Find the directional derivative at this point. All right, so here's the answer. So, like I said, the direction where the gradient is maximum is the same direction as the gradient itself. So therefore, we have to compute the gradient. And then you differentiate this, you get e to the power of y. And you differentiate the same thing with y, you get x e to the power of y. All right. And then so that means at this point, we are looking at only at x is -1, y is 0. So at this point, the gradient is computed as 1, y, to be precise, e to the power of 0, -1 times e to the power of 0. And that's 1, -1. Okay, so therefore, the unit vector is computed as this, -1, 0, 0, times the gradient. And what's this? 1 over. This is the magnitude of this. 1 squared plus -1 squared. Square root times 1, -1. And this is computed as 1 over root 2, -1 over root 2. So that's the direction where the directional derivative is maximum. So that's the answer for the first part, the unit vector u. So this is u. Then now the maximum value here, the maximum directional derivative at -1, 0 is given by what? Well, here, strictly speaking, you may just compute the directional derivative directly, but we already know that the maximum value is precisely the magnitude of the gradient. So at this is precisely the magnitude of the gradient, which we already computed as root 2. Root. Okay, so those are the answers. All right. So let me just give you a couple remarks. First of all, this one, the direction derivative, is now minimum if the direction, the unit vector, is the opposite to the gradient. Opposite to the gradient. Namely, the angle between u and the gradient vector is 180 degrees. And the minimum value of the directional derivative is this guy here. This is the minimum, right? Negative . Okay, that's minimum. And also, that means the directional derivative is 0 if u is what? Now, here, directional derivative is the dot product. And dot product is 0 if and only if those two are perpendicular to each other, orthogonal to each other. So u is orthogonal to the gradient. Then now, with this said, you could interpret the gradient geometrically in the following way. Geometric meaning of the gradient. So let's remember the concept of level curves. Let following be the level curves of z is equal to f of x. So remember, level curves is like a mountain on the map. So you have x-axis, y-axis, and then you have like a mountain, a curve on the map, and then at each curve represents the same elevation, right? And then you are climbing on this mountain, and then suppose you are here, and then like I said, the direction where the gradient, the direction where the directional derivative is maximum is a direction of gradient. But now, what's a directional derivative? A directional derivative, this one, is a rate of change. So that means this one is the maximum when the mountain is steepest, your path is steepest. So you suppose you are standing here and then look at all the possible directions, like many directions, and all the possible, you look at all the possible directions, and then the steepest direction is of course the direction directly pointing to the summit, like this way. If you look at if you look at the summit directly, that's the steepest direction, right? And that direction is the direction of the gradient. So gradient vector here is this vector here is a gradient vector. The direction which is the directly pointing to the summit. And of course, if you look at the opposite direction, in a way that's the steepest, but steepest going down. So that's the minimum rate of change. Smallest negative, but it's because it's negative. And that's where the direction derivative is a minimum. And of course, if you look at the direction which is perpendicular to the gradient, that's when the directional derivative is 0. The directional derivative is 0 means you are not climbing the mountain. Actually, your elevation doesn't change. Oops. And of course, that is this direction. That's when this is tangent to this level curve. So that means, after all, gradient, which is a vector, is orthogonal to the level curve at each point. So that's the meaning, that's a sort of geometric meaning of the gradient. Then now, using this idea, actually, we have small applications, which we don't really care much about in this course, but let me mention it because there are a few exercise problems for your homework. Now, let's consider functions with 3 variables, namely similarly, given w is equal to f of x, y, z, then the gradient of big F is computed as f sub x, f sub y, and f sub z. That's fine. And then this one is orthogonal to the level curve. But what is the level curve in this case? Well, it's not going to be a curve anymore because level curve is for z is equal to f of x, y. For this, fix z is equal to k, let's say, and then you get the level curve at the elevation k. That's the idea of level curve. Now we have function of 3 variables. So in this case, it's not a curve anymore, but actually it's a surface. It's called a level surface. Namely, at w is equal to some fixed number k, you get the level surface for each w is equal to k. And I get the surface, so that means if you are given a surface like this, the gradient vector is perpendicular, orthogonal to the surface. That actually gives you a normal vector to the tangent plane at the particular point. Namely, the picture is like this. Suppose you have a surface given by, this is surface given by big f of x, y, z is equal to some particular number k. And then if you pick up some particular point ABC on the surface, and then if you compute the gradient of big F and plug in particular number ABC, what you get is a vector perpendicular to this surface. So therefore, here gradient of f evaluated at ABC, which is the vector where x component is a partial with x, but you plug in ABC, and then plug in ABC, and then this is the normal vector of the tangent plane. Remember, we have seen tangent plane before. Now this is another formula for tangent plane at this to the surface at this point ABC. So therefore, the equation of the tangent plane is written this way. ABC x minus a plus fy ABC y minus b ABC z minus c is equal to 0. So this is the equation of the tangent plane to the surface at ABC. So this is a tangent plane. So this is another formula for the tangent plane. Also, there's a concept called normal line. To the surface at ABC. Namely, here's a surface f of x, y, z is equal to k. And then you have a point on the surface. And then, like I said, we have the gradient vector, which is perpendicular to the surface. Then now, if you look at the line going through AB, perpendicular to the surface, then this is called the normal line. Then now, what's the direction vector of this normal line? Well, as a direction vector, you could choose the gradient vector at this point. Normal line and with direction vector, the gradient. So therefore, the equation of this normal line by symmetric equation is written this way. F sub x ABC is equal to y minus a f y ABC, and I is equal to z minus, I'm sorry, this is b, minus c divided by fz a b c. Okay, so this is the equation of normal line. We are not going to really see those two things, normal line and maybe we see this one, but normal line. But there are some exercise problems for your homework, so you can just use this formula. Anyway, so that's all about the section. Which section is this? Section 14.6.